Okay, thank you for the introduction. So I was told that we should give an introductory talk at the beginning of the workshop for the local community, but since nobody is here except the participants of the conference, I will try to improvise and skip the most basic things in the introduction in hope to tell you more about the recent results. And the outline of the talk is, I will begin with the setting. Then, well, the plan was to define Eisenstein series in detail, but I will just introduce the notation. Then I plan to define automorphic forms. Well, in view of this introductory talk, I thought to follow the title of the workshop. So I have Eisenstein series automorphic forms and the cuspidal support. Then I will come to Franke filtration. Which is the let's say the tool for the new method for proving holomorphy of Eisenstein series. And then I come to section 5, which are applications. The last word in the title of the workshop. And then finally, I will present a new method for holomorphy of Eisenstein series. Okay, so as I said, the first 3 sections I will do more quickly than planned. So in the setting, we work over an algebraic number field, so we will fix F, an algebraic number field. A will be the ring of adels. Of F and I consider as in Franke's paper G to be a reductive connected linear algebraic group over F. Then we will usually denote by P standard parabolic. P is a standard parabolic subgroup of G. And this is the Levy decomposition. So L is Levy factor. And the unipotent radical. And here I mean standard with respect to some fixed choice of the minimal of a minimal parabolic subgroup. Let me, since at the end I will give an example in the case of GLN, I will just write somewhere here. Example. So in case of G equals GLN, I will choose the minimal parabolic subgroup to be upper triangular matrices, and then P are block upper triangular, and L is just block diagonal isomorphic to a product of GLNs. And okay, I will not even write the unipotent radical. It is just identities along the diagonal, and then identity matrices, and then something above the diagonal. And what else I need? So then I will denote, but by APC check, the space of complex parameters for my Eisenstein series. This is simply the Z module of rational characters of P tensored over Z with C. And whenever I have some so this is a finite dimensional vector space over C. Whenever I have some element of this space, I will identify it with a character denoted by nu S underline of the Levy factor of the given P. Okay. And so this is the parameter space for my Eisenstein series. In this space, we have also the notation APC plus check, which is the positive file chamber. Given by the choice of the minimal parabolic subgroup, and APC plus check bar is its closure. And in my example, if the sizes of the blocks, they are given here. If the sizes of the blocks are n1 to nk, the space APC check is isomorphic to C to the k. And now given some k tuple of complex numbers, this nu S underline of, so if I take here L1 to Lk to denote elements of this product, then nu S of this element is absolute value of the determinant to S1 times absolute value of the determinant to Sk. Okay, this is how this identification works in the case of GLN. Okay, now I can go to section 2. Okay, and now I will immediately skip the, for the introductory version of the talk, I had here definitions of cuspidal representations, residual representations, and these things. Now I will skip all this and just fix the notation for the Eisenstein series, because I assume that most of you are aware of the definition. So but I want to take capital Pi to be either cuspidal or residual automorphic representation of let's say L of A. So this is the Levy factor of the given parabolic. Residual, I mean, this is, okay, I can then, so I look at L2 automorphic forms, decompose into discrete and continuous spectrum, and then for residual is just the complement of cuspidal in discrete spectrum. So I will now go to the example. These are exactly the Speer representations, what I call. And then I take, so I start either with a cuspidal or residual automorphic representation. So usually you construct Eisenstein series with cuspidal automorphic representations, and this construction with residual automorphic representation, if I start with a residual automorphic representation, then this type of Eisenstein series will be called the degenerate Eisenstein series. To distinguish. And so I also need S underline, an element of this space of complex parameters. Okay. And now to construct the Eisenstein series, I define the space W pi. This is the space of functions on G of A mod N of A L of Q. And then for normalization purposes, I divide out also the connected component of the maximal split torus of the center of P, the Archimedean place. L of F, yes. Sorry, I thought I'm preparing an introductory talk, and then this was here. I also have to put Archimedean component. So I worked over Q originally. That's sorry if I make sometimes a mistake. You see, such that for every G in G of A, the function on L of A given by L is sent to F of L of LG belongs to pi isotypic component of L2 discrete. So this discrete part of the spectrum of the group. And then we, using these functions, we can construct Eisenstein series by taking into account also this complex parameter by twisting this function f by the character given by the complex parameter normalized by the half sum of positive roots in the unipotent radical of P applied to an element of, so this is a character of the Levy factor, and this L comes from the Iwasawa decomposition of G. And the value is independent of the choice of the Levy part of G. And then we denote the Eisenstein series associated with this capital pi and this complex parameter by E of S underline G. F is the chosen function in W pi. And I also put in the notation the capital pi to know from which representation this Eisenstein series is built. This is the sum over gamma in G of F over P of F of this function Fs underline of gamma G. Yes? Yes, this is, but this is already in Langlands, I think he does. And there is also a paper by Franke Schwärmer in Mathematische Annalen. This is I think 1997, right? I think it is correct. And then there are some standard properties of these Eisenstein series, which is that the sum converges in some cone deep enough. So converges. Should I write this? Converges in some cone inside the positive Weil chamber. Continues analytically to the whole space APC check, and the poles in the closure of the positive Weil chamber are along a finite, locally finite, sorry, family of singular hyperplanes. Okay. So let me now perhaps continue, and then I will come back to the example. So to explain what are the Speer representations in the GLN later when I come to the applications. Okay, now I'm done with section 2, and I go to section 3, automorphic forms with cuspidal support. Now I will use, so we are working with automorphic forms in the sense of Borel-Jacquet Corvallis paper. So let me just briefly recall. So a function on G of A is an automorphic form if it is smooth as a function on G of A. Second, f of gamma G is f of G for all gamma in G of Q, G of F, and for all G in G of A. And then I need some technical conditions, K finite, for where K is chosen maximal compact. Then I need that it is Z finite, where Z is center of universal enveloping algebra of the Lie algebra of the infinite part of like the Archimedean part of the group. Complexified, yes. Let's say that this is okay. And and certain growth condition of uniform called the uniform moderate growth. Okay. And so this is our definition of automorphic form, and we denote by A the space of all automorphic forms on G of A. Here we have. Well, it's smooth. Yes, I can do both because smooth condition gives you K finiteness at p-adic place, but I can also make it like this, yeah. Yeah. Okay, and now so we have the space of all automorphic forms on G of A, not only square integrable forms, and we would like to understand this space because it is in many applications it is not sufficient to work with L2 space with the square integrable forms. And there is a decomposition of this space along the cuspidal support. So when I fix a parabolic P with the Levy decomposition L times n of G, and then I fix Pu to be a cuspidal automorphic representation of L of A. Which is a component of L2 cusp in our previous notation. So I call it pi u to stress that it is not some cuspidal representation that is twisted. It is really a component of L2 space. And for the twist, I fix S0, so an element of this parameter space. But in the closure of the positive Weil chamber. This is because when you fix a cuspidal support, you can conjugate it, and then you can always assume that the parameter belongs to the closure of the positive Weil chamber. This simplifies the study of this space. And now, using this unitary cuspidal representation in L2 and this parameter, I form a representation pi, which is pi u twisted with this character of the Levy factor corresponding to S parameter SU. And we can form the Eisenstein series. E of S underline G F P U associated with this pi u, just like in this construction before. So this time this is a cuspidal Eisenstein series coming from this cuspidal representation pi u. F is a function then in the space W pi u as before, and S is in the parameter space. Okay, and we are interested in the analytic properties of this Eisenstein series at this given evaluation point, this fixed parameter. So S0. And because this parameter is chosen in the closure of the positive Weyl chamber, there is only a finite number of singular hyperplanes passing through it. And so we can cancel these poles along finite number of singular hyperplanes by some polynomial. And this means that there exists some polynomial, call it of S underline in k variables, such that when I multiply this Eisenstein series with this polynomial, this is holomorphic at this point that we are interested in, this S0 underline. And then we can define finally the space A, P, pi. This is a little bit cheating in the notation, abusing. So this is actually a space corresponding to some associate class of these representatives, but I just in the notation keep the representatives P and pi. This denotes the space of automorphic forms with cuspidal support in this P and pi, and it is defined as in Franke-Schwärmer paper that I already quoted, as the span of all coefficients in the Taylor expansion of this holomorphic function around S0. Okay? So this is quite different than the definition of Meglen-Walsperger, who study really the constant term of Eisenstein series along different parabolics, and in terms of this constant term define the cuspidal support. But as proved in Franke-Schwärmer, these two definitions are equivalent, and for me in this talk it is easier to, since I already have defined the Eisenstein series, it's easier to define it in this way. The reason why these two definitions of the cuspidal support of automorphic forms are equivalent is precisely the Franke filtration. So I will now go on to define the Franke filtration, and you will see that essentially, not essential, but really all automorphic forms are Eisenstein series or derivatives of Eisenstein series, which follows from the filtration which is defined by Eisenstein series. And this is the reason why you don't have to look at the constant terms of Eisenstein series. You can just take the Eisenstein series with appropriate data and kill all the poles, and all the coefficients together give us automorphic forms with this given support. I pick one of them. Yes, but I can choose whatever I need later when I study holomorphy of Eisenstein series at the end of the talk. I will fix as 0 the point of evaluation in which I want to prove that the Eisenstein series is holomorphic. So you can choose it. In the definition, it's fixed because this is a part of the cuspidal support. So it's we fix P, pi u, and the parameter. Okay. It's easier to, because if you fix only pi u, then S0 can vary. But I want, in the applications, I really want to fix it, because in every application I compute, for example, if I compute cohomology, I have the evaluation point coming from some conditions on non-vanishing. Okay. It's hidden here in pi. Yes, that's true. Okay. Sorry, it would be better that I write it PS0 or something, but yeah. Okay. So it is unitary cuspidal and then the parameter which is fixed. Okay. Much water. Huh? Okay, so now I come to section 4, Franke filtration. So now I will define the filtration, not very complete with all the technical details, let's say, but to give you the idea how it works, and then we will see in the application how in the application section how we can use it to do different things. So the Franke filtration is a finite filtration. And now of the space of automorphic forms, but you need to put some finiteness condition, and so that it becomes really a finite filtration. The space of all automorphic forms is too big to be considered as a whole. So what we do, we fix the cuspidal support, because in applications this is what we are interested in, and define the Franke filtration only for this piece of the space of automorphic forms. This is different than Franke. So Franke has a different way to make the filtration finite. I will explain just in a couple of minutes. So a finite filtration so our approach is to, and this is the approach also in Franke-Schwärmer. Paper. So we need a finite filtration of this space with a fixed cuspidal support. Unitary part and S0, everything is fixed. Original Franke approach is different. He looks at the space called AJ, which is a space of automorphic forms annihilated by a power of J, and J is an ideal of finite codimension in this center of the universal enveloping algebra mentioned before. So what is the difference? This approach is convenient for like theoretical considerations. If we want to prove some general facts, then you fix a J. This J, for example, if you have in mind applications in cohomology, this J is coming naturally from the coefficient system. And fixing such a J makes the filtration finite and describable, let's say. But if you want to make explicit computations, so really use this fine structure of the Franke filtration, this is still too large. Let's say you don't have a like explicit description of the filtration, and that's why we need to fix this cuspidal support. Okay, and then with the fixed cuspidal support, we can really do very explicit description. For an example, you can see my recent paper which will appear in Memoirs of AMS on SP2 or SP4, however you call it. So in which the Franke filtration is completely described for all cuspidal supports in this simple case, just to see what can happen in this what different orders of the quotients can happen in this small example. And then you can see how explicit this can all be made. Okay, but let me go back now to this space that we are now interested in. So so the Franke filtration is, well, some kind of finite filtration. I will just make some notation for it. So so let's start with like AP pi 0 to be the full space, and then go down, and then L will be the length of the filtration, L plus 1 in fact. And the main point of this filtration is that the consecutive quotients in the filtration are isomorphic to some parabolically induced representations. And the second main point of the filtration is that this isomorphism is given in some way by Eisenstein series. And because this is a little bit technical, but because these two facts are needed to explain the method for proving holomorphy, I will now go in a little bit of more detail, not too much. Yes. It's tensored with some, yes. Yeah. Because it's a globally induced representation, so it's yeah, I think so. Yeah. Okay, so now what are the ingredients in the definition? So the main ingredient, let's say, is certain set denoted by MP pi. This is the set of triples I call it them R, capital pi, Z underlined, where R is a parabolic. I always assume the parabolic subgroups are standard. So a standard parabolic subgroup of G containing either P or associate parabolic to P. So you remember that we fixed not really a specific parabolic P, but the associate class of parabolic. So essentially, R should contain an element of this associate class. Then pi is residual or cuspidal, let's say, is discrete spectrum representation of L2 discrete of the Levy factor of this parabolic R. So LR is the Levy factor of R. And Z underline is in the closure of the positive Weyl chamber given by this parabolic R in the corresponding space of parameters, such that pi tensored with this, twisted by this character nu corresponding to parameter Z. So this capital pi is again unitary, as just like this pu, pi u here. It is really in L2, and Z is certain twist of this capital pi. And to stay in this space AP pi, I must suppose that this pi tensor with nu Z underline is has cuspidal support in P pi. Okay, not to be in a wrong space. So okay, and so now using this on this set of triples, the key, let's say, so this is first, and then the key, let's say, Franke insight is that you can define certain partial order. So Franke defines partial order on MPI, and then we have to define these steps in the filtration. We have to choose T, function T, from this set of triples to integers. And you have freedom of choice, but you usually instead of Z, you use here some set from 0 to the length of the filtration, so that the names of the steps are consecutive integers, which respects this partial order. Okay, so this is the most technical part of the talk, because now this function actually gives you which triple corresponds to which filtration step. And now you can just say what this AI is. So this is isomorphic. Well, there is certain co-limit in the category of representations taken over this R pi Z, such that T of R pi Z equals to I. Okay? Of the induced representation from parabolic R of pi tensored with, twisted by nu z underline, and then tensored with the symmetric algebra of ARC check. Okay, so these are the induced representation that appear. The co-limit here is sometimes a direct sum, sometimes we have to do some quotients. This co-limit appears because we have functional equations of Eisenstein series. So if we take all the induced representations without taking care of the co-limit, then we would count twice, like, let's say, equal Eisenstein series, which are related by the functional equation. And that's why there is some this is just some technical notion. But this is the thing is that we have this induced representation, which describe, I mean, the co-limit of several induced representations, perhaps, that describes this quotient. Now, how this isomorphism is really constructed in Franke's paper is the following. So remember that when we defined Eisenstein series, we took f in w pi, and we took a parameter z, and then we constructed the function fz. Fz is, in fact, an element of this space. It can be this f, a different f, twisted by z underline, exactly belong to this induced representation. And this is how sometimes the Eisenstein series is defined, by taking a section of the induced representation. And what is this symmetric algebra? This symmetric algebra can be understood as the algebra of partial derivatives on the parameter space of the Eisenstein series. So a typical element here is some partial derivative with respect to some parameter space f. Alpha is some multi-index. Okay, and so now what we do? So z is some fixed parameter in the triple that appears. But instead I take fs, where s is varying parameter. So I take essentially fs is a section of this induced representation when z is replaced by a varying s. And then I want to evaluate at z. And taking this tensor, what Franke does to make this isomorphism, he constructs the Eisenstein series, starting with pi, parameter capital pi, parameter s underline, and we would like to evaluate it at z underline, okay? The point which is given by these triples. So everything, this works if the Eisenstein series is holomorphic. But if the Eisenstein series has a pole, then, sorry, I forgot something here. It is not sufficient to look only at the Eisenstein series to get all automorphic forms. We need also to take derivatives and then evaluate at S underline. Okay? But again, if Eisenstein series has a pole, then the derivatives will also have a pole, and we could not evaluate this Eisenstein series at the point of evaluation. What we need to do is what Franke calls we have to take the main value of this expression at z underline. And what is the main value? The main value, I will just not write a lot, I will just tell you. So the main value is the following. So we have a complex meromorphic function which has a pole at z underline. So since z underline is in the closure of the positive Weyl chamber, there are only finitely many hyperplanes, singular hyperplanes passing through z underline. And we can choose any direction which is not along one of the hyperplanes, so not tangent to any of the hyperplanes. And along this direction, this becomes a function in one complex variable, and we can write down the Laurent series. Okay. it depends on the direction, right? So changing the direction changes the Laurent series. But and Franke would like to define the main value as the constant term, so A0 of this Laurent series. The problem is that this A0 is not well defined. It depends on the direction you choose. But it is, so this is well defined as an element of the quotient. So the key of the proof of the Franke filtration is to show that whatever direction you choose, the principal part of the Laurent series always belongs to a lower, deeper filtration step. And then these negative coefficients in the Laurent series are treated as elements of the quotient. So A0 is well defined up to these negative elements. And that's how he essentially proves that all this, okay? So that the point is that he has to choose this partial order in such a way, so the key is in this partial order, in such a way that whenever you have an Eisenstein series with the pole, the principal part of the Laurent expansion belongs to a deeper filtration step. It can be deeper filtration steps, but there must exist some lower filtration step here. Okay. Yes? Well, usually the smallest subspace is the square integral, like the residual representations. Okay, and then well, yeah, yes. Well, it is not. We have examples where the order of parabolics is interchanged, so it is not really. It's in my paper with Grobner in Israel Journal in case of GLN already. So you cannot say that given the rank of parabolic that you know the order. But let's say if the pole is of higher order, then it is probably in a deeper filtration step, but not in general. This is not a theorem. This is just some feeling, let's say, as you asked. Yeah. In the case of a maximal parabolic, you have if you have a pole, then you have two steps of the filtration. The square integrable part is the deeper, and then the rest is the upper. Okay, and now I have 6 more minutes, so I should. Let me now first do section 6, let's say, to show you the method. This is the key observation. So the key observation is that when the Eisenstein series has a pole, then there must be a deeper filtration step where the principal part of the Laurent series belongs. And so we have the following idea. So the problem is show that some Eisenstein series constructed with some IU, let's say some. This is some degenerate Eisenstein series in general, constructed from some discrete series representation pi, show that this Eisenstein series is holomorphic at S underline equal to some given S0. Okay, or let's call it Z0 because S0 is the cuspidal support. So I have any Eisenstein series degenerate for any group, and I need to show it is holomorphic at some specific point. Then step 1 is to find the cuspidal support. So find p pi so that this Eisenstein series belongs to a p pi. Okay. Step 2. So this Eisenstein series is given some pi, which is pi is a representation of some Levy factor of some parabolic, and it has to be evaluated at some z underline. So this degenerate Eisenstein series corresponds by its construction to some r pi z, some triple, belonging to this m p pi, this set of triples for the cuspidal support that we determined in step 1. Okay. And in step 2, we have to study the position of this triple in the partial order. Okay. And then step 3, if r pi z is maximal in partial order on m p pi, then our Eisenstein series is holomorphic at S equal the underline. Okay? Because, and this is exactly because of this construction of Franke. So, first step is easy. We just find the cuspidal support of the given Eisenstein series. We can always find its cuspidal support. The second step depends on the setting, depends on the situation, whether we can understand the partial order or not. And in the third step, we just have the conclusion if we find here that the position of this triple is that it is maximal element in this partial order. What is the proof? The proof is extremely easy, knowing all this. So if this Eisenstein series had a pole, the Laurent expansion would have negative elements, which means they should belong to a lower filtration step. But if this triple is maximal in the partial order, there is no lower filtration step where these negative elements of the Laurent series could belong. And that's how we conclude that this step 3, in this step 3, that this Eisenstein series is holomorphic at Z. Now, let me just finish in 2 minutes. So, once having this idea, which is very simple, knowing all this machinery of Franke, my question was, is this useful? I mean, could we get some, what is the scope? What points can we do? And then I saw a paper by Ginsburg and Sudri about the degenerate Eisenstein series of GLN, in which they give a very nice description of the poles in terms of linked segments of Bernstein-Zelevinsky. And I wanted to check if it can be obtained also in this way. It turns out in the example of GLN, we get all regions of holomorphy. So it is completely complete description, but our method cannot determine poles. So we rely on Ginsburg and Sudri to see that where are the poles. The remaining points which are missed by this method are really the poles. We just see that the triple is not maximal and we cannot conclude anything. So we just can prove holomorphic points. We cannot find poles with this method. And their paper is in the case of two, like induction, Eisenstein series coming from two Sper representations. And then as a next step, we studied arbitrary degenerate Eisenstein series on GLN. And really, it works perfectly. It gives you all the holomorphy, all holomorphy points for the case of GLN. Of course, this method does not see DL functions. So if we go away from GLN, for example, in SP2N case, then the pole depends on non-vanishing at 1/2 of some L function. It depends on whether the representation is orthogonal or symplectic. And all these things are not seen by the partial order. So we can just hope to find holomorphy regions away of these critical points. But that's it. Okay, and now I will, obviously, section 5 I will skip. I will just say a couple of words, what are really the applications. So first, from this construction, Franke already proved that every automorphic forms can be obtained in this way, because this is the filtration. So all automorphic forms are Eisenstein series or derivatives of Eisenstein series. Second, he proved that the cohomology of arithmetic groups can be computed using spaces of automorphic forms, because using Eisenstein series, he constructed a spectral sequence. And in long years of my collaboration with Joachim, we did many explicit computations using the Franke filtration of cohomology, of automorphic cohomology and cohomology of arithmetic groups. Besides this work on holomorphy of Eisenstein series, there is a work in progress with Harald Grobner in which we extend the Jacquet-Langlands correspondence to the space of all automorphic forms. Because Badulescu, some years ago, finished the Jacquet-Langlands correspondence story by proving the correspondence of the discrete spectra between GLN and the inner form. And he also gave a counterexample that this cannot be extended, but at the level of irreducible components. And these quotients are not irreducible. They are naturally described in terms of these triples, which are discrete representations of some Levy factors. So if you do the Jacquet-Langlands for the triples, you can essentially get the Jacquet-Langlands for the whole space of automorphic forms by transferring the quotients of the filtration as a whole, not going inside irreducible parts. Okay, sorry for the overtime, and I will finish now.